So today's session, the sessions are sponsored by Premier Resources and OpenSync Technology. So today's session, it's going to be handled by mainly Igor Bagno, and I'm probably going to do something at the end, not that long. But Igor is a reservoir engineer. He has 15 years of experience in reservoir engineering in multiple fields around the world, from characterization, numerical modeling, analytical modeling. And he has a career initially he started in Gazprom and then also worked for some time in Total. And the past few years, he has fully dedicated to consultancy, working in consultancy firms in London, in particular Exodus and also Synergy. And Igor has been an independent consultant and also associate of Premier Resources for the past five years. And so today we are going to talk, or the session is going to be focused on geothermal, as you may know, or you may have already seen. And the purpose is to have an overview of geothermal as a source of energy. Also, Igor has been gathering quite a few interesting case studies to talk about the different type of geothermals and what are the facilities and what are the kind of workflows in this type of studies. And then I think he will move into doing some Monte Carlo simulation to estimate the potential of a geothermal project, estimating based on a P10, P50, P90 power output using a Python library that he will cover in a bit. And finally, I will spend some time talking about a library that we found also interesting, which is for the modeling of thermal systems. And in this case, I'm going to show a very simple power plant that we can create from scratch. And then we can have a look at a more complicated power plant and how we can estimate the power plant output. So without further ado, I think I'm going to give Igor the control. Yeah, Igor, you can start sharing.
Thank you. Hello, everyone. And thank you for joining our session today. We hope it will be interesting from different aspects. We'll try to make it interesting. So here's the topic for my part. It's Python applications assessing the potential of geothermal projects. So initially the interest came through one of our clients' request, and we both agreed on that some of the things are quite similar between oil and gas and geothermal in different areas. The area of exploration, operations, evaluation, and assessment, and also entering that business is possibly quite similar to what the people are used to do for a number of years. Although the geothermal energy as such is quite an old technology, and in some instances might be older than oil and gas actually. So one of the first power plants, it will be surprising, but the first power plant started in 1904 in Tuscany in Italy. So as oil and gas industry moved faster, some of the things were captured from oil and gas sector, and therefore we share that common interest with the people we talk to, and we started to investigate on what actually is feasible and what capabilities can we develop and advance in order to be able to help clients in evaluating these opportunities. So the agenda for me for today. I will briefly describe the difference between the low temperature and deep geothermal projects. I have one example of low temperature application in southwest France, and deep geothermal projects examples from Latin America, from El Salvador and Guatemala. And as Alejandro mentioned, there is an overview and a case study that we prepared using one of the libraries that we found in Python and worked a bit with it, which helps to assess the potential of geothermal project based on volumetrics and Monte Carlo. And I'll show you the Python demo. To start with, I'll start with the low temperature geothermal case study, and we came across the consortium, which is called MEET, for enhanced geothermal systems. So this is a European consortium, which is largely focused on helping and supporting the projects to advance technologically in terms of the research, but also in terms of getting finance and interest to these projects. It's essentially around Belgium, here in the UK. There is one project in Cornwall of a deep geothermal project, which was in its active phase in 2018 and 19. And there is one interesting example by a company called Vermilion Energy in southwest France. This is a Canadian company, but operating in France. Quite a few fields operating there, oil fields. And the advantage of low temperature geothermal applications that they found is that very little investment needs to be done, and it can be actually handled on a conventional oil field, which is in production and producing oil, but also water. So they use the water, which is hot eventually. It's always hot when it produced from the oil reservoir, to provide the heat to the greenhouse, which was nearby, and to the residential area, and also to the high school. And briefly to describe it, so it's not far from Bordeaux and Arcachon Lagoon. There are two fields called Les Pins and Les Arbousiers, and the production is from both actually, but the oil and water treatment and separation is handled on the one in the south, and then the water is sent to the north to hit the high school, takes the water which is produced from the field in north and taken back into the main facility to be reinjected. So it's reinjected in the cold condition, and also there are shallower reservoirs which are also colder than the reservoir which is in production. And the study that Vermilion performed was investigating the effect of that cold temperature wave on the temperature, or on the downhole temperatures, on the water temperatures in their producers, to ensure that actually all the obligations, contractual and others, are respected, and they will be able to still produce and deliver the heat to their customers. And that presentation is actually available on YouTube as well. You will find the link at the end of the presentation. It's a separate one, so I will not stay on it for a long time. But essentially, the model was conventional because it was prepared already for that field, which is the southern one, and it was built in T-Navigator, and all they needed to do is basically add the thermal option, put the parameters in for the rock and fluids, the thermal parameters such as heat capacities, heat conductivities, and perform a thermal simulation essentially, which is done by a senior reservoir engineer in Vermilion, and he was able to do it without any further deep learning or deep advancement. But a vast overview of the data formed by him, and that included the temperature measurements, the water chemistry measurements, in this field historically, to understand the historical performance, to history match and make a forecast. So we looked at it, and basically pretty much everyone who works with us and in our company, have some experience in thermal simulations, mainly for the EOR, like steam injection, steam floods, evaluating the potential of EOR projects, but using also the simulation. So we told ourselves it's not a problem of doing the same. So to advance with that capability, it's actually quite interesting to be involved, and it gives quite a good results, and quite quickly. So this is low geothermal. So the principle is you take the water for to heat to provide the heat. It's not used for the power generation. So for anything which is power generation, the temperature at the reservoir conditions should be somewhere near 200 degrees, 150 degrees minimum Celsius. For low geothermal, it can be lower than that. It can be 100, it can be 70, it can be something around it, but depending on the infrastructure, depending on the distance to the customer, etc., etc. But we thought that that was an interesting example to show. So next is the deep geothermal projects, and this is where a more thorough evaluation and investigation is required. And we looked at the areas. Well, I mentioned Italy. Historically, this is the area where the geothermal power generation was in place. But other area which was developed starting from 70s is the Latin America, and mainly all the countries which are along the Central American volcanic arc. So basically, the people were looking after the indications of hot reservoir water, and the indications were volcanoes, were hot springs. So, and this is the entire area, which is quite large in the countries like Salvador, Costa Rica, Honduras, and Guatemala, and further on. If we take an example of El Salvador, it's actually quite significant proportion of the power generated from geothermal resources. It's up to 25% of the country's demand. And there are two plants which are in operations. One is Ahuachapán, and another one is Vermilion. On Ahuachapán, I'll stay a bit for longer. I have a bit of details on that field and its exploration and power generation capability. So here we go. We have a Pacific Ocean, we have a coast, we have all these volcanic arc chain of volcanoes basically following the coastline. And all you need to do is to explore the areas which are around it, and make surveys, explore, and then try to drill and find the resource of heat. So this is these are the pictures from a site visit by one of experts from the company called Lageo. They're available also on online. You will find the more photos if you follow the references at the end of the presentation. But this is essentially to show that the project in El Salvador was quite old. It started in 1975, but all the facilities are there since that time. Nothing changed. The project is ongoing, and Here we have the examples of the main facility, the turbine, which was Japanese, provided by Mitsubishi, power transfer facility, and the control room. And here are the turbine and the power generator by Mitsubishi, which is there since 1976. So the project was initially funded by World Bank, and its capacity is 95 megawatt, and it has 3 turbines, two of them are one flash, and one of them is a double flash, which means they take steam. You take water, you draw pressure, you generate steam, it passes through the turbine, you generate electricity. Then it's still at quite some high pressure. You drop the pressure a second time, you generate steam again, and you go through a second turbine and provide electricity, generating electricity again. So there are 52 wells drilled in this field, reaching the depth of 645 meters, 14 vertical producers and 6 directional, and 9 reinjectional wells. The rest of it is used for monitoring. Another country which we looked at is next to El Salvador. So we looked at Guatemala and looked at the existing power generation projects, the power plants, and also at the exploration projects or projects which are under re-evaluation. So again, the resource-based potential is quite high. It's possibly higher than in El Salvador, but as the country is bigger, the overall proportion of the energy which is generated by geothermal is lower. So it's 3% only. So there are 2 plants called Zunil and Amatitlán, operated by Ormat, which is a US-based company, which has quite a large portfolio. If you follow that company, that will be quite interesting. They have a very good website with the power plants all across the world, in New Zealand, the US, Africa, Latin America, of course, and it's tens of projects that they put on stream since 70s. And some of them are running still, and some of them are just installed. It's quite fascinating. So in Guatemala, there are more than 10 geothermal projects which remain at the feasibility stage or are under evaluation or re-evaluation. And there are about around 14 geothermal areas which are under investigation. But geothermal potential remains largely underdeveloped for the various reasons, and one of them is it's risky. Basically, from the engineering perspective, you need to find the source of, like in oil and gas, you need to find the source of hot water. You need to find the reservoir, and the reservoir should be permeable. It should deliver. So the wells that you drill, you need to test and be able to produce and be able to re-inject. So you basically produce the hot water or steam, and you re-inject the cold water to support the pressure and to maintain the pressure and to keep the project ongoing. So there are these 3 factors are quite difficult to find at the same time. So some of the reservoirs will be fracture dominated. It can be anything which is from granite, any hard rock which is fractured and contains hot water or steam, that will do. Sediment-based reservoirs, like in oil and gas, it can be, again, limestone, sandstones, whatever. But again, you need a reservoir which needs to be proved permeable and needs to be proved fine for re-injection. So the Amatitlán, and I'll start with the Moyuta and Tecuamburro first. These are the most southeastern areas and which are under evaluation still, or were under evaluation. So it's Moyuta first. The area is quite large. Again, it was explored in 1975. The area is around 330 kilometers. This is the Guatemalan Institute for Electrification, which initiated exploration first, and they followed basically the volcanic complex and northern flank of the Moyuta dome to a depth of 1,000 meters. Results were unfavorable at that stage. Project was abandoned, but then it was re-evaluated by, again, the same institute and Los Alamos National Laboratory in 1990. So they proposed the new relocations, performed the isotopic data review, review of the samples of the gas and water, and there was evidence of a deep reservoir presence with fluid rising convectively along the axis of the volcano. And structurally, it was controlled by the north trending faults. So the idea was to explore the areas where the main body of that dome was intersecting these north trending faults, and actually look into the areas which were, well, faults are good for the say dissipating the system, but not good for the maybe blocking. Again, all that question about the sealing or non-sealing faults. But that project, well, again, it's still not not complete. So the exploration stopped at that point in time, and it's still there, the resource. Tecuamburro, another example, which is just 50 kilometers southeast of Guatemala City. And from the point of view of surface exploration, there are various geothermal manifestations like fumaroles, boiling springs, mud pots, and even there is a large acid sulfate lagoon called Laguna Ixpaco. And surface exploration was done again by Los Alamos Laboratory and the Guatemalan Institute for Electrification in the 80s and 1991. So they did the field mapping, they did the volcanological studies, geochemical sampling, and analysis of springs and fumaroles. They drilled a core hole to a depth of 800 meters, but the presence of the reservoir was not confirmed. So the rock was impermeable, although the temperature was good. And then the project was evaluated by a Japanese company in 2005. They reviewed all the available data, performed the magnetotelluric survey, which helped them to understand better the distribution of that water resource. Basically, helped them to map the resource based on resistivity measurements. And they recalculated the potential for that resource of 50 megawatt for a project which could last for 30 years. And two projects which are in place, which are in operation, again operated by Ormat. One of them is called Zunil, Zunil 1 and Zunil 2. Here you can see the very nice picture of volcanoes and very beautiful picture of that plant in place. Initial estimate was the capacity of 24 megawatt for a binary plant for 25 years. Binary means that you use you have a working fluid. You don't generate steam from the liquid from the water that you produce, but you have thermal exchange between your working fluid, so it's a closed loop between thermal exchange between the working fluid and your hot water that you produce or steam. So plant was commissioned in 1999 with a higher capacity, But then the production of water in relation to steam dropped. Reservoir performance was not as good as forecasted, and they couldn't maintain the pressure enough, and some additional capacity was moved elsewhere. So the current capacity is 23 megawatt only. And another example is Amatitlán. So again, same area and located just 40 kilometers south of Guatemala City. And there are 4 wells drilled by a Japanese company, confirming presence of the system with quite a high temperature, estimated resource 50 megawatt for 30 years, and a binary plant was built in 2007, but the current capacity is 20 megawatt only. So now we're moving to the principles of the assessment of the potential. We're talking in megawatt units here, but this is a measure which is can be perceived as a volumetric parameter rather than we're saying megawatt electric, but megawatt is energy, the amount of energy in the system, and system can be different. It can be a thermal system, and the thermal system in this case is this hot water reservoir. So essentially what we need to understand, like in oil and gas projects, we need to understand the volume and the mass. So we need to understand the area, the thickness, the density of rock and fluid to get to the mass. And then we need to get to the specific heat capacities of fluid and rock. That can be done based on the cuttings, laboratory measurements based on the cuttings, and that is essentially quite well understood, the heat parameters. So for the reservoir to evaluate the pore volume, we need porosity, and we need temperatures. Well, the reservoir temperature and the abandoned temperature, which is around, again, the minimum temperature, which will allow the whole system to work. So from that, we calculate simply the amount of energy which is stored in the rock, again, by the area, by the volumetric assessment. Same for water. And for the plant capacity, for the plant potential, we basically take the total heat which is in the system, and we take an assessment. We make an assessment of the recovery factor of the heat, essentially, and the conversion efficiency, which depends on the type of the plant and the plant configuration. And there are 2 other factors, which basically the plant net capacity, basically the efficiency of the plant, the time that plant is in operation, and the time of the project, the lifetime. When we get to the question of the resource and reserves evaluation, again, we are quite close to what we are used to take as a standard for the reserves classification. So reserves notions are the same, reserve categories are the same. We're talking reserves and resources here. We're talking also probable, proven, possible, depending on the how sure they are that the resources there. For the reserves to be there, the well needs to be drilled. It needs to be proven economic. It needs to be proven technically feasible and economic, and it needs to need to have access to the license to operate. Everything which is around or nearby the proven area can be thought as probable reserves, and any areas which are, again, maybe undrilled, but we understand the potential of the resource. We understand the we have indications at the surface. We have an evaluation which is done. We have a plan to operate, a permission, and the economics are working. So we're talking resources here, but in a quite high category. And everything which is just indications is an inferred resource. So to show you the another point which is important in the exploration is that we need to make sure that the heat source is well understood, its nature. So largely, most often, it is the internal earth heat flows which provide the constant energy to the system, but we need to understand how far they are. We need to understand how aquifers are working. We need to understand how aquifers are connected, and this is all based on the water chemistry. This is all based on the temperature measurements downhole. But it's important to understand the nature of the heat source, and if it's able to provide the heat flow. So we move into the case study example in El Salvador. We're back in Salvador again, and there is an area which is near the existing power plant. There is a dam which generates the electricity there, but there is an area which is next to the dam, which is called Nombre de Jesus, and it's quite a large area. And we are taking the parameters from the area, from the exploration projects which was done there. And I'll move to Python soon to show you how the Monte Carlo library that we found works. So in this particular example, we have an area estimate. Well, again, we have distributions for each parameter to do statistics, to do the Monte Carlo. So the area estimated is between 5 and 6 kilometers square. Thickness 450 to 600. Reservoir temperature from 130 to 163. Porosity, we have an estimate. And the distribution, we have a specific heat capacity values for the rock and the water. We have densities. We have an estimate of the recovery factor, which is again the function of the type of the reservoir, if it's fracture dominated or sediment based, and this distribution is quite fair. So even if it's quite complex projects to characterize, complex reservoirs, recovery still can be somewhere 10% and 25% at the maximum. Conversion efficiency depends on the type of the plant. Again, we mentioned binary plant and flash, and different stages of flash. You have a type of the system which is called organic ranking cycle, which helps you to optimize the system and use latent heat from the steam which is already past the turbine. So you're using the hot steam, which is you're using the heat from the steam which is already generated the electricity, and you're using it to heat the rest of the system. Efficiency for the power plant can be around 90-95%, and we're estimating the projects, evaluating the project for 25 years. So I'll move to the